In this mini lecture, we're going to have our first look at how we can use the fundamental theorem of calculus to evaluate integrals. So this is going to go under the heading of rules of integration. So just as we have for differentiation, we have a list of rules for how to evaluate integrals, the same way as we have a list of rules for helping us to evaluate derivatives. So here's the story so far that we have really with integration. Well, there's an awful lot left out here, but we're at this really important point that we've had a look at this fundamental theorem of calculus part 2, saw some examples where we can see that this is how we can evaluate integrals. Right. They'll have all kinds of applications as areas, as lengths, as volumes, and as integrals that tell us how to solve certain equations that will predict the evolution of various systems. Right, so our theorem tells us that if we have a continuous function f defined on an interval a, b, then to evaluate the integral corresponding to the area under the graph of f, if it's a positive function, what do? We find an antiderivative, capital F of little f, and then we evaluate at the endpoints and subtract. Okay, so that's easy to say, but it can be very hard to do. The difficult bit there is to look at the function little f and from that be able to figure out what the antiderivative capital F should look like. Okay, so that's our major job, and we're going to spend quite a bit of time looking at that, trying to get to grips with this question: how do we find an antiderivative capital F for a given function little f? The good news is that there are some basic rules that help us out. Okay, and that's what this mini lecture is going to be about, looking at some of those basic rules and looking at them in practice. We need to understand a really important point first about antiderivatives. Antiderivatives are sometimes called indefinite integrals. Okay, so definite integrals, well, definite integrals are called definite because we know exactly where they are, but they're between x equals a and x equals b. Indefinite integrals are somehow, well, we don't know exactly what interval we're dealing with. But really, the key thing is that an indefinite integral is just another word for an antiderivative. In other words, a function that turns into a given function when we differentiate it. Okay, we need to understand one very important aspect of antiderivatives. Okay, I know how to differentiate things, so I can see that this function capital F is an antiderivative for this function little f. Okay, and you can check that easily enough. Because when I calculate capital F prime, I leave the 2 alone. I differentiate x cubed, I'll get 3x squared. And when I differentiate 4x, I get 4. So that, sure enough, is equal to 6x squared plus 4. Okay, so I'm happy that this function capital F is indeed an antiderivative for little f. Because when I differentiate capital F, I get little f. Okay, fine. On the other hand, this function capital F is also an antiderivative for little f, because when I take that function capital F and differentiate it, I get 2 times 3x squared, I get plus 4 when I differentiate 4x, and I get 0 when I differentiate 11 because it's a constant. So sure enough, this is equal to 6x squared plus 4. This is equal to little f. So there's another antiderivative. There's another one. Because when I differentiate this function capital F, I'll get little f of x. You can perhaps see the difference between them. It's just that there's a constant number there. Well, there's a 0 in the first one. And it's not hard to see that that's kind of always going to happen. I can always just chuck in a constant number, because when I differentiate that constant, it'll go away. So if you give me one antiderivative, I can add any constant number and I'll have another antiderivative. And then you could add another constant number and it would still be an antiderivative. So if we have one antiderivative, there's actually infinitely many other antiderivatives, all of which just differ by constant numbers. Okay, so really when we're asking for an antiderivative, in some sense we're asking for all antiderivatives. And there's no increase in difficulty between doing those two tasks, finding one and finding all, because the only difference is that we have to add on a constant number. Okay, so we use this integral symbol without limits to represent the collection of all of the antiderivatives of f. And that collection is called the indefinite integral of little f. Okay, so no limits. So we're not dealing with a definite integral. We're not dealing with an area under a curve. We're just using this symbol to say, okay, this is the collection of all different functions that turn into little f when you differentiate them. And those differences are very minor. It's only going to be that we've added on a different number, a different constant number. And the way we write this down is to use, so just continuing with the example that we're looking at here, we write that the indefinite integral of 6x squared plus 4, well, I find one antiderivative, and I'm using the first one here, so that in some sense is the simplest. I write down one antiderivative, and then I write down plus c, where this capital C is called a constant of integration. And the idea then is that any and every antiderivative of this function must look like that. It must be equal to 2x cubed plus 4x plus c for some constant number c. So in this example here, we see that the capital C is equal to minus 11. In this example here, the capital C is equal to plus 87. Okay, so just a bit of notation and a new definition, a new term to get used to there, the idea of an indefinite integral. This plus c is really, really, really important. It has to be there. Our answers in some settings will simply just be wrong if we don't have the plus c. So anytime we look for an antiderivative, we're looking for an indefinite integral, and we always make sure to put in the plus c. Okay, so that's what the second last bullet point is saying. It's saying that every antiderivative of little f equals 6x squared plus 4 has the form capital F equals 2x cubed plus 4x plus c for some number c. Okay, so that's just some sort of background information. Now to the basic rules of integration. And these rules, certainly the first two rules, really tell us that when it comes to integration, life couldn't be easier. What does this say? It says to find the indefinite integral of some constant number c multiplied by a function f, well, I can just pull out the number c and then do the integration. So in some sense, we ignore constants. This is very similar to a rule that we have for differentiation. If the function g of x is equal to c times h of x, well then to differentiate g, I leave the c alone and just differentiate the h. So we have this result that's very similar to a rule of differentiation. Okay, so what this means in practice is that when we see a number in front of some x's, we can ignore the number and just deal with the x's. Another very, very convenient fact of integration is that if we integrate the sum of two separate functions, or a better way to understand this is if our function is naturally made up of the sum of two different objects, maybe that's 2x cubed plus 4x. If our function is made up of the sum of two different things, we integrate the things separately and then add the results. Nice and handy. Here's a commonly occurring example, the integral of a constant. If we integrate a constant, what will the answer be? The answer will be k times x plus a constant of integration. How do we know that? Well, I check that if I differentiate this here, I'll get k. And sure enough, differentiate k times x, I get k. Differentiate the constant number c, I get 0. So there's our indefinite integral of a constant number k. So sorry, I should have written that down. That k is constant here. Oh, sorry, it's written. It is already mentioned there. Okay, so here's our first somehow interesting example of an antiderivative of a non-trivial function. And we have this really useful result that we can actually work out by knowing about differentiation, by working backwards from differentiation. The integral of x to the power of n is x to the power of n plus 1 divided by n plus 1 plus the constant of integration. Now, you have to be careful. If n is equal to minus 1, this result is not true. When n is equal to minus 1, we would have that integral there, the integral of 1 over x, that's x to the power of 1, right? And this rule does not apply in this case. Okay, so we need something else to deal with that example. But for things like the integral of x squared, the integral of x to the power of 17, the integral of the square root of x, which is the integral of x to the power of 1/2, we can use this rule. And sorry, that's terrible because I should have dx is written down all the way along there. Okay, so for all of these examples, we can use this rule here, which, like I say, comes from reversing the corresponding rule of differentiation. Okay, so if I know how to integrate powers of x, I know how to integrate constant numbers, I know how to integrate sums and multiples, well, I immediately have a huge list of functions that I'm able to integrate. And here's an example of that. Okay, so this complicated looking thing, we integrate it by finding the antiderivative, and we find the antiderivative by following the rules that I've got here. Now they're all scribbled over, but let's we'll come back and use them at the appropriate times. Okay, so how do we evaluate this? Well, first of all, I notice that this function is made up by adding up various bits. There's 4x to the 7 minus 9x cubed plus 11x minus 6. So the first thing to do really is bear in mind that we're going to integrate each bit separately. So this integral will equal the integral of 4x to the 7 dx minus the integral of 9x cubed dx plus the integral of 11 times x dx minus the integral of 6 times dx. So we're using that add rule, the integral of f plus g is equal to the integral of f plus the integral of g, to do each part separately. As a next step, we can use the first rule on the previous slide, which tells us that we can just ignore the number. So the 4 skips out to the front and we have integral of x to the 7 dx. The 9 skips out to the front and we'll have the integral of x cubed dx. The 11 skips out to the front and we'll have the integral of x dx. And the 6 skips out to the front, or rather, in fact, we can use the third rule that was written down there. The integral of k dx is kx plus constant of integration. So we'll have 6 times x plus constant of integration. Okay, for our next step then, we'll use the rule that we had on the previous slide, that the integral of x to the power of n dx is x to the power of n plus 1. So the power increases by 1, and then we divide by that new power, plus our constant of integration. So what do we have there? I put that in brackets. X to the power of 7. I increase the power by 1 to get 8, divide by the new power 8, and add on constant of integration. Minus 9. Integral of x to the power of 3. I increase the power by 3 and to get 4, and then divide by the new power, plus our constant of integration. Plus 11 times integral of x. X is, of course, x to the power of 1. So that will be x to the power of 2 divided by 2 plus our constant of integration minus 6x plus c. Okay. Now let's deal with the x's, and then I'll come back and deal with the constant of integration. So I have 4x to the 8 divided by 8. That's 1/2 x to the power of 8 minus 9 over 4 x to the power of 4 plus 11 over 2x squared plus minus rather 6 times x. Now, the constants of integration. There's a little bit of subtlety here, I suppose, maybe. Each one of those symbols, C, represents any constant number. So I have in here x to the 8 over 8 plus a number, x to the 4 over 4 plus some number, x squared over 2 plus any old number, 6x plus any old number. And we can put them all together and just rename them all together as C. Right? So I'm looking at this whole thing here. I found this antiderivative for it, doing one step at a time, doing one part at a time. And then at the very end, I can add in the constant of integration. But it is really important to add that in at the end. Okay. absolutely crucial. But we can leave it until the very end. So it isn't absolutely essential to throw them in here, 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 and here, and here, provided we have our constant of integration at the very end. Now, this looks a bit weird because I'm using, what I've written down there is literally incorrect, because I have, on the previous line, I have 4c minus 9c plus 11c minus c, and here I have just a c. But we have to remember what that c represents. It represents any number. Let's just check. When I differentiate this, differentiate x to the 8, I get 8x to the 7 by a half will give me 4x to the 7. There's a minus sign, which is good to see. And we have minus 9 over 4. Differentiate x to the power of 4, I get 4x cubed. Minus 9 over 4 times 4x cubed gives me 9x cubed. 11 over 2x squared, differentiate it, I'll get 11 over 2 times 2x, which gives me 11x. Differentiate 6x, I get 6. So I'm happy with my result. Okay, so there we are using, there's an example of using the first basic rules of integration to evaluate really a non-trivial integral there. And we could then use that to measure areas on the graphs, or maybe it's a length of a curve, or maybe it's some other application. Now, one of the key ideas for answering that key question, given f, given a little f, how do we find the capital F such that capital F is an antiderivative for the little f? Well, part of this is just to remember some of the rules that apply to different functions, like remembering rules of differentiation. So here's our first entry in a table of integrals. Okay. So literally tables like you see in the book of mathematical tables. Okay, so here's our first one that you will just need to know and remember. Okay, now we can prove these things using the definitions. For our purposes, the important thing though is that you just know how to implement these integrals so you can solve problems using them. So the integral of k of the e to the k times x, the exponential function. Well, we can check by differentiating on the right-hand side that when I differentiate 1 over k times e to the kx, we get e to the kx. So there's our indefinite integral of e to the kx, 1 over k times e to the kx plus constant of integration. Integrating sine x gives minus cosine x. We need to be careful with the sign. Integrating cosine x gives sine x. And this is as it should be, because we know that the dual results, when I differentiate sine x, I get cos x. And when I differentiate cos x, I get minus sine x. So we just need to be very careful about the signs there in these results for integrals. You can just double check there that these results tally with one another. Okay, so now here's another few functions that we're able to integrate. So I can now answer a question like this. Evaluate the definite integral of 2 times e to the x plus 4 times sine x. Okay, so here I'm using part 2 of the fundamental theorem because I have a function little f equals 2 times e to the x plus 4 times sine x. My first step is to find an antiderivative, find any antiderivative here, any antiderivative whatsoever. I leave the 2 alone, and my rule for integrating, remember the integral of e to the kx dx is 1 over k e to the kx, k times x plus c. In this instance, I have 1 times x, so k equals 1, so I'll have just 1 over 1. And that's 1, of course. So the integral of e to the x is e to the x. I'm not putting in the constant of integration yet. Next bit, I can leave the 4 alone and integrate sine x, and I remember that that should be minus cosine of x. And I could just check that by differentiating. This time I'm going to put in a constant of integration. Okay. Well, of course, I'm supposed to put in, I need to put in the constant of integration to make sure that I have all possible antiderivatives. So I'd have 2e to the x, minus 4 times cos x plus some constant c. Now, the fundamental theorem tells me then that to evaluate the definite integral, I need to calculate f when x equals pi. So I have 2 times e to the pi minus 4 times cosine of pi plus the constant of integration. What's the constant of integration in this example? Well, I don't know, but let's just leave it there for the moment and I won't worry about it. So that would be 2 times e to the pi minus cos of pi is minus 1. So that's plus 4, plus that constant of integration. The lower limit, f at 0, I have 2 times e to the 0 minus 4 times cos of 0. Sorry, that's place there. I have 2 times e to the 0 minus 4 times cos of 0 plus the constant of integration c. E to the 0 is 1, so I have 2 times 1. Cos of 0 is 1, so that's minus 4 plus that constant of integration again. Okay, so the definite integral then, the answer, the integral from 0 to pi of twice e to the x plus 4 times sine x dx is f at pi minus f at 0. And tidying that all up, well, actually I should have on the previous line noticed that that was equal to minus 2 plus c. So f at pi minus f at 0 is 2 times e to the pi plus 4 plus that constant of integration minus 2 plus the constant of integration. So I get the result 2 times e to the pi plus 6. And the constants of integration cancel out there. Okay, I have c minus c. Now, in definite integrals, the constants of integration, in fact, are always going to cancel out. So I don't actually need those. Because what does the fundamental theorem tell us? It tells us, one of the things it tells us is that we can use any antiderivative. So just need to be careful here about distinguishing between using any one single antiderivative and the previous problem of finding all of the antiderivatives. Okay, but let me just recap quickly on the key points there. I started with the function little f. I used the rules of integration and the tables to figure out the antiderivative. I can check, and indeed I should always check that I've got the antiderivative right by just differentiating this function here and making sure that I get 2 times e to the x plus 4 sine x, which I will. I'll put in the limiting values, the endpoint values, and subtract to get the result there for the area under the curve. Just do this one very quickly, evaluating this definite integral. Now, this is picking up on the indefinite integral that I calculated a few moments ago. So I can immediately write down the indefinite, the antiderivative here that we got from the example there a few moments ago. And here, I'm just going to double down on that idea that I mentioned a moment ago. I don't need to add on a constant of integration in this example, okay? Because the fundamental theorem part 2 for evaluating definite integrals tells me that I can use any antiderivative. Why can I use any antiderivative? Because I get c minus c, like we saw in the previous example. So there's an antiderivative for this function. I evaluate it at the right-hand endpoint. X equals 1, so that's a half minus 9 over 4 plus 11 over 2 minus 6, which would be, let's put that all over 4. I'd have 2 over 4 minus 9 over 4 plus 22 over 4 minus 24 all over 4. And see if I can figure that out. So I have, oh, there's a nice handy 22 plus 2, 24 minus 24. So I have minus 9 over 4 for f at 1. F at 0, very conveniently, is just 0 because I have x's all the way through. X equals 0 gives me f of 0 is equal to 0. So there's our answer for that definite integral there. The answer is minus 9 over 4. Okay, so that's the end of that sequence of lectures about the fundamental theorem of calculus, parts 1 and 2. Where does it come from? Understanding that in terms of area functions. And then most importantly, perhaps, the idea of how to use the fundamental theorem of calculus and tables of integrals to actually evaluate integrals. We'll be looking at more of that in the next sequence of lectures.